Hello. In this lecture, I will go over simple distributed load and how to simplify it and reduce it to a force at a distance. First, let's look at what does it mean to have a distributed load. So, in real life, almost everything is a distributed load. You are probably watching this video right now, sitting on your couch, laying in your bed, or sitting at your office chair. Your weight on the couch, on the chair, on the weight is a distributed load pushing down. Same thing, a pile of bricks on a workbench or on a beam create a distributed load that kind of looks like a triangle. Books on the bookshelf, they create approximately a rectangular distributed load. So now we want to see how can we simplify these systems and kind of start solving them. So here I have a schematic of a beam with a distributed load of Wx. So this is function, meaning an equation of x. So one axis is load, let's call it newtons. One axis is x, let's call it meters. And we have a distributed load with units of Newton per meters, meaning every meter of the beam is subject to W amount of load. For example, 100 newtons per meter, meaning every meter is subject to 100 newtons. A load like this could be, I don't know, minus x2 plus 30, something like that. Meaning the beam at distance x, any point at distance x is subject to this equation amount of load. Okay, so the goal here is to get rid of this distributed load and just replace everything by one FR located at a distance which we can call it x bar. So this is the goal. The goal is to reduce, simplify, because we know how to handle FR, a force on a beam, but we don't want distributed load. So the goal is to simplify it. In order to do that, we use an area element that you can see here. It's a tiny sliver of the area. It looks like this. It has the width of dx and it has the length of w. So this little area here, which is differential amount of force, so a tiny sliver of force, which is the same as element of area, is W dx, width multiplied by length. So this force F will produce a moment about point O, right? We learned about moment. So moment of this force about point O, we gotta find the total. So the total, let me write it this way. dF produce a moment of dF multiplied by distance. It's located at distance x about point O. So now let's find the total moment about point O. The total moment about point O, I like to call it equation 1. Total moment about point O is integral of all of that, summation of x df, and let's replace df by this amount that we have, is x w dx. Okay, so let's look at the figure 2 in the bottom one. We said that the goal is to get rid of that system, replace it by this FR at a distance, meaning these two are equivalent, meaning the effect of both of them should be the same. So this FR should also create the same moment if they're equivalent, right? This FR should create the same moment about point O. So that means FR multiplied by a distance, perpendicular distance, and that is x bar. But let me see, what is FR? FR is summation of all those df's. I can't use summation. Summation is for finite number of things. Instead, I have to use integral. Integral of df, because we have infinite number of df's. Okay. And this is a linear integral, integral over length. df, again, I have it up here. I'm going to replace it by w dx, which is also entire area. Okay, so integral of df is integral of the area, which is area. Okay, so let's put FR back up here. So FR is now integral of x bar w dx. Okay, both of these are equivalent or same moment. So let me write it here quick. I have mr equals integral of x bar w dx, which is, and this is linear, x w dx. So x bar from here is going to be x w dx over w dx. This is linear integral, which is the same as integral over area of x dA over integral of dA, because this is dA. Okay, this x is what we call centroid, which is geometric center of area under loading, which is this area right here. So let me just simplify it here. Again, goal is to replace distributed load by a single force at a distance x bar. Force FR, let's look back quick here, is the area under loading. Area under loading. But don't forget, don't let the area kind of mislead you. The area mislead you. because this has units of meter, this has units of Newton per meter. So the unit is going to be Newton meter, meters, it's going to be newtons or pound. That's FR. X bar, which is the centroid, location of the force, is the centroid of that area. Some people like to write it like this, total area, which is correct. So the force is area under load, location of it is the centroid. So that's a general equation that we're going to use to simplify. A lot of times the distributed loads have a simple shape. Has like this top one has a rectangular. So again, the goal is to replace it by F. F, area under curve, X bar, centroid of area under loading, not under curve. This area, the length is 10 feet. The width is W, which is 400 pound per foot. These two get canceled. So FR is 400 pounds, as you can see it. Centroid of an area, centroid of a rectangle is in the middle of it. So half of 10 feet is going to be located at 5 feet from point A. From A. And as you can see, they get rid of the distributed load, replace it by one FR located halfway. Second one is a triangle. Again, same thing. FR is area of triangle, which is half of its base multiplied by 600 Newton per meter. Meters, 3, 6, 1800 newtons. That's my FR. X is located at 1/3 of 6 meters from base. Let's call this X bar 1. It's from the base, which is 2 meters from base, which is point B. Or it's located at 2/3 from A, which is located at 4 meters from A. Both ways are correct any way you want to do it. The only important thing is, remember, centroid of a triangle is located here. 1/3 this way, 2/3 this way. So for problems involving distributed load, if they are rectangle or triangle, you can just simply do this very quickly. But if they include a curve like this one, a 2 or 3 degree polynomial, then you have to do the integration to find both FR and X bar. Thank you.